This tiny line looks harmless. But the kernel of a proof assistant cannot check this line as written. The line is full of missing information. Some of it is obvious to us. None of it is optional to the kernel. The missing step is elaboration, the translation from the code people write to the explicit terms the kernel checks. Today, we are not mainly asking how terms compute. We are asking how proof assistants recover the term you meant. This episode pulls together a design problem that shows up across proof assistants and dependent type implementations. The question is broad. How does a proof assistant turn user-friendly dependent type code into a precise term? The trusted kernel is deliberately small. It checks variables, lambdas, applications, pi types, universes, inductive types, and eliminators. That smallness is a feature. The smaller the kernel language is, the easier it is to trust. Surface code of a proof assistant is not that small language. It has notation, holes, implicit arguments, pattern matching, overloaded constants, type classes, and tactics. So proof assistants split the job. The elaborator may be clever. The kernel must be strict. Many arguments are real arguments even when they are hidden at the surface. The braces are a user interface choice. The core term still contains the types alpha and beta. From the list E1, 2, 3, the elaborator infers that the element type is nat. From ED, it infers that the result type is the same. What looks like one short expression becomes a fully applied constant with hidden parameters filled in. Elaboration is not only bottom-up, it also uses the type expected by the surrounding context. The annotation says the right-hand side should be a function from nat to nat. That expected type tells the elaborator what type X has. To see why elaboration leans on expected types, it helps to compare two classical algorithms for recovering type information. The first is Hindley-Milner, the algorithm behind ML in early Haskell. Take a small example. A function that applies its first argument to its second. No types are written anywhere. First, every unknown gets a fresh type variable. One for f, one for x, one for the result. Walking the term collects equations. The one application f counting forces a single equation. The type of f must be a function from the type of x to the result. Unification solves all the equations together. Then, at the binding, the variables still left free are generalized, turning apply into a value usable at any types. For the simply typed lambda calculus with let polymorphism, this is enough. Every well-typed program has a most general type, and the algorithm finds it with no annotations at all. But once polymorphism can appear under a function arrow, or once types can depend on terms, complete inference becomes undecidable. Hindley-Milner cannot reach dependent type theory on its own. Bidirectional type checking takes a different route. Instead of inferring everything, it splits the typing judgment into two modes. Some terms synthesize a type upward. Others are checked against a type that flows in from the context. Variables and applications already carry their type, so they synthesize. Lambdas and constructors need an expected shape to know what they mean, so they run in checking mode. A term that synthesizes can always be used in a checking position. Compare its inferred type with the expected one. Type annotations flip the other direction, turning a checking position into a synthesizing one. This is the deep reason dependent type systems use bidirectional checking. Annotations are not attacks on the user. They feed the elaborator exactly the information it cannot guess. Hindley-Milner would accept this. It gives Sx a fresh variable, infers the body, and generalizes the result to the polymorphic identity. A dependent elaborator does not. It never invents a binder you did not write, so the type of X stays an unsolved metavariable. So a bare lambda is given a way back, an explicit domain annotation that synthesizes, or an expected function type that flows in and lets the elaborator check the body. Real elaborators blend both ideas. Bidirectional checking shapes the recursion, metavariables and unification, a generalization of the Hindley-Milner trick, fill the unknowns that remain. When the elaborator does not yet know something, it creates a metavariable, a temporary unknown. Then type checking generates constraints. As constraints accumulate, metavariables get solved. A hole is a visible metavariable. Around it, the elaborator can still infer useful information. Here, the missing function must accept a NAT. This is why editor tooling can show the goal at a hole. The hole is not outside the type checker. It is part of elaboration. Some unknowns are not just missing types or missing values, they can be missing functions. In an equality substitution, the elaborator may need to infer a whole predicate, sometimes called the motive. This is why higher-order unification is both useful and expensive. The system is not only solving for a symbol, it is guessing a whole context with a hole in it, and several different contexts can fit. Lean's elaborator handles many of these cases because they appear constantly in dependent proofs: substitution, induction, recursion, and dependent pairs. It can afford this because it never attempts the full problem. In complete generality, higher-order unification is undecidable. Huet showed that no algorithm always decides whether a solution exists, and that when solutions do exist, there can be infinitely many of them. The way out is due to Dale Miller. Restrict attention to the case where a metavariable is applied only to distinct bound variables. Then the equation has exactly one solution, and finding it is cheap. Just abstract the right-hand side over those variables. This well-behaved case is the pattern fragment, and solving only it is called pattern unification. Developed by Miller and refined by Fenning, it is the backbone of higher-order unification. When a problem falls outside this fragment, the elaborator postpones it, hoping that other constraints pin the unknown down first, and turns to limited guessing only as a last resort. Their algorithm is organized around constraints. Some constraints are easy equations, others create choice points. A name may be overloaded. A definition may or may not be unfolded. A higher-order problem may have several plausible shapes. When a later constraint fails, the elaborator can return to an earlier choice and try another branch. A useful strategy is non-chronological backtracking. Failure is tracked to the assumptions it actually depends on, instead of blindly undoing the most recent step. This is the engineering heart of elaboration. The elaborator must be helpful, but it also has to stop before the search space explodes. Now reduction enters the story. Elaboration often needs to know whether two types are the same after computation. A vector of length 2 plus 2 should fit where a vector of length 4 is expected. This is the conversion rule. If a term has type A and A is definitionally equal to B, the same term may be used at type B. The computation rules are the familiar ones. Beta applies functions. Delta unfolds transparent definitions. Zeta opens let. Iota computes eliminators on known constructors. Conversion is the part of type checking that runs computation while comparing types. Elaboration uses it whenever the types only match after reducing a definition, a function application, a let, or a match. Delta reduction sounds simple. Replace a name by its definition. But doing that everywhere is disastrous in a large library. In this design, unfolding is a controlled elaboration choice, not a reflex. Lean's early elaborator used reducibility hints to keep search predictable. Some names behave like abbreviations. Others should stay opaque during difficult unification. These hints guide elaboration only. Once a fully explicit term is produced, the kernel still checks it with the ordinary rules. The token zeroer is not one kernel constant. It is notation that elaborates differently depending on the expected type. In Lean, numerals elaborate through type class machinery. The surface syntax is simple because an instance argument is being found behind the scenes. The same is true for place. The elaborator must know which type X has before it knows which addition operation to use. This is useful automation, but it is not kernel magic. The final term contains the chosen operation in the chosen instance. Type classes can synthesize data, not just notation. For an if over a proposition, the elaborator needs evidence that the proposition is decidable. This is one subtle case where type class search, computation, and ordinary type checking have to cooperate inside one elaboration process. Some systems also let the elaborator insert coercions, small conversions between types that users would find tedious to write. If an expression has type A, the context expects B, and a coercion from A to B is registered, elaboration may insert it. A coercion is not the same as conversion. Conversion says two types are already the same by computation. A coercion inserts an actual function. This distinction matters because inserted functions remain in the explicit term that the kernel checks. Pattern matching feels primitive, but in Lean's core, the trusted primitive is the eliminator. The elaborator compiles the match into an eliminator application with a motive and one branch per constructor. Recursive definitions go through the same kind of translation, plus a termination check. The surface definition is accepted only if it can be justified by structural recursion, well-founded recursion, or another trusted discipline. Once the match has become an eliminator, iota reduction explains how it computes on a known constructor. This connects back to the inductive types episode. Constructors build values, eliminators consume values, and elaboration translates friendly pattern matching into that core structure. Tactic scripts are not proofs the kernel understands directly. They are instructions for constructing a proof term. At the start of the by block, Lean creates a goal. You can think of that goal as a metavariable whose type is the theorem we still have to fill. The tactic intro refines the goal by introducing a hypothesis. Then constructor refines one goal into two smaller goals, one for each field of the conjunction. Each exact command fills one metavariable with a term of the required type. When no goals remain, the tactic block has produced a proof term. So tactics sit above elaboration. They manipulate goals, call elaboration on the terms they produce, and eventually hand the kernel an ordinary explicit proof. This boundary keeps proof assistance usable without making the trusted core enormous. Powerful automation lives above. Small checking lives below. Elaboration is powerful, but it is not a theorem prover for every true statement. In lean s plus 0, n minus n reduces by definition. But 0 plus n has n has the recursion on the wrong side, so a variable n usually needs induction or a library theorem. This is the practical split. Elaboration fills structure. Conversion handles computation. Proofs carry mathematical content. When the system asks you for more information, it is usually because one of those boundaries has been reached. Return to the line from the beginning. It was never just 3 tokens. It asked the elaborator to infer hidden types, propagate expected information, solve metavariables, choose meanings for overloaded syntax, and produce a core term. The central lesson is that elaboration is not one trick. It is a coordinated constraint-solving engine around a small, trusted kernel. That is the real shape of modern dependent type checking. The user writes a compact program. The elaborator recovers the explicit proof term. The kernel checks that term using typing rules and trusted computation.